Hello everyone, Mr. Fussett here, and we are back for part 2 of our lesson involving the mean value theorem and Rolle's theorem. We actually discussed Rolle's theorem in part 1, so if you haven't listened to that video, make sure you go back and watch it, or you can watch it after this video because it's not necessary to understand Rolle's theorem to understand the mean value theorem, even though they are closely related. But we are going to scroll down. And this time, instead of me giving you the theorem first and then you thinking about the different parts, we're going to go through an example and then kind of build the theorem from that example, or try to generalize this example to all examples that have these characteristics. So we're given a function, and it says draw the secant line between f of 1 and f of 2. So we're going to go ahead and do that. First going to plot those points with some color. So f of negative 1 is up here at 2. F of 2 is all the way up here at 5. And we're going to draw a secant line. It's pretty straight. And part B asks us to find the slope. So I'm just going to use these 2 points. Let's label them first, negative 1, 2. And we've got 2, 5. Slope is equal to f of negative 1. Oops. I'm not even going to do, we already have those points labeled. We're just going to jump right in. I've got 2 minus 5 all over the quantity negative 1 minus 2. So that's going to give me negative 3 all over negative 3, which is going to be equal to positive 1. Which makes sense because the line has a positive slope. So number 3 says, is there another point along the interval, the closed interval negative 1 to 2, where the derivative is also equal to the slope of the secant line? Sketch some examples to help. So pause the video, see if you can find a point where if you drew the tangent line through it, and I would encourage you to go ahead and sketch a tangent line, or a couple of them, where it has the same slope as that secant line that we drew. So can you find a spot where the tangent line looks similar to that secant line? Well, it's going to be somewhere to the right of 0, and it looks like it's going to be somewhere, oops, it's not very good. Could be somewhere along here where the tangent line is also going to have a slope of negative 1. Right? We don't have to, it doesn't ask us to find the exact x value, it just asks us to try to determine whether there is one. And there is. This is essentially what the mean value theorem says. Right? If we have a function, and it's got to be continuous, just like Rolle's theorem on the closed interval, it's also got to be differentiable. If those two things are true, then the slope of the secant line through the 2 points on the end of the interval, well, there's going to be some x value where the slope of the tangent line has the same slope as the secant line. And that's what the mean value theorem says. Again, think about mean, right? It means average. So this theorem, it's an existence theorem. It's saying that there is going to exist a tangent line that is the same, that has the same slope or the same value as the average rate of change of the function over the given interval. All right, so let's really think about what that means. On the interval negative 1 to 2, well, the average rate of change is 1. Right? As I move over 1 unit on the x, I'm increasing on average 1 unit on the y. Well, all the mean value theorem says is that, again, there's going to be at least one spot where the tangent line has the same slope as the secant line, or where the tangent line slope is the same as the average rate of change. All right, let's write that down, and then we will start to apply it. All right, so again, I color-coded the initial conditions, or the hypothesis of the theorem, with the conclusion. If f of x is continuous on the closed interval a to b, and differentiable on the open interval a to b, then there exists a c on a to b, the open interval, such that f prime of c, so the derivative at c, is equal to Well, the slope of the secant line from A to B, which is f of b minus a, all over b minus a. Okay, let's look at applying this. You know what? Actually, before you do that, here's a question for you. Why does, and maybe we'll talk about this in class, why does f of x need to be differentiable here as well? Why does it have to be differentiable for that c value to exist? Think about it. Maybe sketch some examples to help you out, but think about why that is. All right, now we'll move on. Let's see, we're going to do this page. I'm going to leave number 6 for you all to do on your own, I believe. So it says, consider the function h of x is equal to 3 minus the quotient 5 over x. A portion of the graph of h of x is pictured to the right. And we're being asked to determine, does the mean value apply on the interval -1 to 5? So we don't have to figure out what that x value is. We're just trying to figure out, can we use the mean value theorem to say that there is an x value where the slope of the tangent line is equal to the slope of the secant line. So we got to run through our criteria, right? There's only 2 of them for the mean value theorem. Is the function continuous, and is it differentiable on the respective interval? So if we just look at the graph, we may not get the entire story, right? Because this graph is only a portion. It doesn't show the function what its value is at x equals 0. It doesn't show what the function's values are when the x values are negative. So we definitely should pay attention to the algebraic form given up here. And that's what I would go off of to determine whether it's continuous versus differentiable. So let's just start with continuity. Is the function continuous over the closed interval -1 to 5? Well, we see a denominator with the variable in it, right? So we need to check where is that denominator going to be equal to 0, if ever? Well, it's going to be equal to 0 at x equals 0 because it's just x in the denominator. And then we need to think, is 0 on this interval -1 to 5? And it is. So that's going to mean we can't use the mean value theorem. We just have to, state why down here. So no, and we can abbreviate this MVT, mean value theorem, is not applicable on the closed interval -1 to 5 because h of x, h of x is undefined at x equals 0, and 0 is on the closed interval -1 to 5. Again, a couple different ways you could write this, use some different words, but the idea has to be there. You have to talk about where this function is undefined and that makes the function not continuous over the entire closed interval. All right, for part B, does the mean value theorem apply on the interval 1 to 5? Well, the only place it's not continuous is at x equals 0, and that's not in the interval. So we can say 1, h of x is continuous on the closed interval 1 to 5. This one we could look at the graph for, right? Because we can see that the graph is continuous over that closed interval. Now we need to check for differentiability on the open interval. So we could look at the graph, and the graph does show us that we can take the derivative because it's a nice smooth curve with no vertical tangent lines on the open interval 1 to 5. But we can also check out the derivative and see if that's ever undefined over 1 to 5. So let's just look at that. H prime of x, derivative of 3 is 0. If we take the derivative of -5 over x, we are going to get +5 over x squared. And you could go back through and work that out with all the steps if you wanted to. Maybe rewrite it as negative 5 times x to the negative first power, apply the power rule, then rewrite it as a quotient. But for the sake of time in this video, we're just going to leave it at that. Again, this derivative is only undefined at x equals 0. So it is defined over the interval 1 to 5, which means the function is differentiable on the open interval 1 to 5. And then we can say thus, MVT is applicable on the closed interval 1 to 5. So now it's asking us to find that x value that satisfies the mean value theorem. We've just proven that there's an x value that exists. Now we need to find it. So we need to find out where the derivative is equal to the slope of the secant line on this interval. So we need to start by finding the slope of the secant line. So slope of a secant line is going to be equal to f of 5 minus f of 1 all over 5 minus 1. F of 5 is equal to 2. F of 1 is equal to negative 2. And you could do that math up here using the actual function. The graph does show that those 2 points run through the exact corners of those boxes, so we can go with that, but you can also check using the original function. Over 4. This gives me 4 over 4, which is equal to 1. So the average rate of change, or the slope of the secant line, is equal to 1. Now we just need to set the derivative equal to 1. We've already found the derivative up here, right? So we're just going to set h prime of x equal to 1, which means we have 5 over x squared is equal to 1. Oops. Come over here, we get 5 is equal to x squared. If we take the square root of both sides, we're going to get two values. We're going to get plus or minus 5 is equal to x. But we have to think about which points are on the interval. Sorry, square root of 5. Which points are on the open interval 1 to 5? Well, negative square root of 5 is not on that interval. So we actually just go with the positive root of 5. That is the x value that we are looking for, the square root of 5. And we can come up here and kind of sketch this out, see if it makes sense. Here's our secant line. And the square root of 5 is something around 2.4. So it's something around right there. And looks like the tangent line matches the secant line around that point, so our answer seems reasonable and we can be confident with it. All right, let's see if there's any more questions on this page for us to do. You know what? I think I'm going to leave both 5 and 6 to you. We've covered enough to give you and based on prior knowledge, you have enough to answer both of these questions, both dealing with the mean value theorem. I do want to harp on one more thing from that previous problem. Make sure that the x value you find is on the interval. All right, so again, sometimes it'll give you multiple x values. Make sure you only pick the one that works. Sometimes there may be multiple x values that work, because the theorem just guarantees that there's at least one. You just need to make sure if you're going to say that that's one that works, it's because it's on the interval. Okay, we're going to cut it off here. As always, enjoy the rest of your day, and we will see you for another video next time.